Hello, everybody. Welcome back. Today we're going to be looking at Unit 8.10, which is all about something called buffer capacity. So we're going to be continuing our discussion on buffers. So let's get started. So if you will recall, the entire purpose of a buffer is to resist changes in pH when things like added acid or base are added to it. And there is a concept called buffer capacity or buffering capacity, which represents essentially how much added acid or base a buffer can take without significantly changing its pH. Because, we talked about how we have in our body systems, we have a bicarbonate buffer system in our bloodstreams, and those buffer systems have a certain capacity. They're not all powerful. If you start chugging hydrochloric acid, aside from a whole myriad of other issues, your buffer has limits to it. It can't absorb massive amounts of ingested hydrochloric acid. So buffers have a limit. They have a capacity as to how much sort of, quote, abuse they can take before the pH starts to change. And if you'll remember, we said in the last unit that if you're dealing with a buffer system, you can use the Henderson-Hasselbalch equation, which is on your equation sheet. The pH of a particular buffer system is determined by the ratio A minus over HA, or base over acid. If you guys will look at the end of the Henderson-Hasselbalch equation, that's that ratio that it's talking about. So the pH of a particular buffer system is determined by that ratio. The buffer capacity is determined by the magnitudes of those concentrations. Okay, and so we're going to see what happens when you change those concentrations. How does that affect the buffer capacity? So if you look at this example, okay, it says calculate the pH of each buffer system below. Okay, and what I'm trying to illustrate by saying HAC here, that's just a shorthand way to say acetic acid. And then this is sodium acetate. So these are definitely buffer systems because I have a weak acid and here is its conjugate base. Okay, so how do we find the pH of a buffer system? Well, we use the Henderson-Hasselbalch equation plus log of, I always just write base over acid. In this case, we're talking about the conjugate base over the acid. Remember, pKa is defined as the negative log of the Ka, and that's given to me, plus log of, and if you look at that first bullet point, we are looking at equal molarities of the conjugate base and the acid. And if we plug all of that into the calculator, we get this for that first buffer system. Okay, so I'm going to write that down. pH equals, 4.74. And again, if this molarity, or that ratio is 1, the log of 1 is just 0, so we end up just getting the pH is equal to pKa for this particular situation. If you look at the second bullet, it is the same buffer system, which means I can use this Ka again. And if you think about it, guys, the math is going to work out exactly the same because that ratio is going to be 1 again. The log of 1 is 0. So both of these buffer systems are going to have the same pH. And if you look back on the previous slide, it says the pH of a buffer system is determined by that ratio. Well, these two bullet points have the same ratio, so they're going to have the same pH. However, it also said on the previous slide, the buffer capacity is determined by the magnitudes of those concentrations. So let's look at something here. Let me write that pH down one more time. For both of these buffer systems, the pH that they would be holding nice and steady would be 4.74. And let's look at this statement. It says, after HCl, which is a strong acid, is added to each of these buffer systems, the first one has a resulting pH of 4.74. Now, stop there. That's really good. Think about it. This first buffer system, just by itself, had a pH of 4.74. Even after adding something super aggressive, like hydrochloric acid, the pH stayed right where it was before. That's a buffer system doing a really good job. Even after adding something really aggressive, the pH has not budged. But it says the second buffer system, this one, after adding that HCl, now has a pH of 4.56. So adding that strong acid has caused the pH to drop a little bit. Which one has the better buffering capacity? Well, hopefully you agree. It's definitely the first one. The first buffer can take more abuse, if you think of it that way. The first buffer absorbed all this acid, and yet the pH remained absolutely where it was before, whereas the second one changed. And what's causing the first buffer system to have a greater capacity? Ladies and gentlemen, it is the magnitudes of those concentrations. The greater those concentrations are, or really what it is, guys, is the greater the number of moles of each one of these participants. Sorry, let me circle just the conjugate base. Okay, the greater the number of moles of these players in my buffer system, the greater the capacity will be. When there's going to be fewer moles of my players, the capacity is not going to be as great. So this is an example of a multiple choice question. I want you to pause the video and see if you can figure this one out on your own. All right, so in this situation, we are creating a buffer system, and it says in order to make this buffer system, I'm going to underline some key bits of information. We need this amount of the acid and this amount of the conjugate base. Okay, but then it says if the student mistakenly mixes, and if you look at the numbers here, compare this set of numbers to this set of numbers. The volume is staying the same, but we're cutting the moles in half. Or excuse me, we're cutting the molarity in half, which as a result means half the moles of the acid. Okay. Look at what's happening to the conjugate base. Compare these numbers to these numbers. The molarity is staying the same, but I'm cutting the volume in half, so guess what? I'm also getting half the number of moles of the conjugate base. Okay, so if you think about it, guys, remember what I said on the last slide. It's really down to the number of moles of the players in your buffer system. And what has happened here, this student has mistakenly added half of the number of moles of each of the players. So if you look at the answer choices and you think about what we've talked about, that is definitely going to lower the buffer capacity. it is not going to create a higher and it's not going to create the same. So I'm going to eliminate answer choices C and D. Okay, so we're definitely going to have a lower buffering capacity. But the reason, what is the reason why? Okay, answer choice B says because the smaller amounts of the acid and conjugate base, which I do have smaller amounts, are going to lower the pH of the buffer. And that's not true, because if you'll notice, I have lessened the acid and the conjugate base by the exact same amount. So remember, the pH of the buffer system is determined by the ratio between these things, and the ratio is going to stay the same. So the pH is not going to change. What is going to change is the buffering capacity. So let's look at letter A and just make sure. The buffer will have a lower capacity, yes, because of the smaller number of moles of acid and conjugate base available to react if an acid or base is added, and that is exactly what's happening. When you lower the number of moles, you lower the capacity, you lower the amount of stuff to react with any added acid or base. Okay, one last piece to this puzzle is sometimes you will be asked to choose a buffer system for a particular pH, okay? And this says the most effective buffers, and again, what does that mean? The most resistant to changes in pH are ones that where that conjugate base to acid or base to conjugate acid ratio is equal to 1, which is true if those molarities are equal, which means, here's the take-home message, guys. When choosing a buffer for a desired pH, you want to choose a buffer system whose pKa is closest to your desired pH. Okay, so sometimes you'll be given a list of possible acids or a list of possible bases. You want to choose a buffer system whose pKa value is closest to your desired pH. Okay, so let's look at a practice problem here. And I'm going to sort of break this down into pieces because there's kind of a lot of words on the screen here. So we have this balanced equation up top. It says the equation above represents the base ionization equilibrium for hydrazine. And then I give you a Kb value. So given a Kb value, that must mean this is a weak base. To prepare a buffer with a pH of around 8.2, 0.17 grams of what's called hydrazinium chloride should be added to 500 milliliters of 0.01 molar hydrazine. Okay, so let's just stop for a minute. Okay, here is hydrazine, which is a weak base. And here is something called hydrazinium, which is its conjugate acid. So ladies and gentlemen, this is a buffer system, okay? Because that you can have buffers with bases and conjugate acids. We are given the Kb value. Let's just review a little bit here. Do you remember this equation on your equation sheet? 1 times 10 to the negative 14th. We are given a Kb value, and I just want to show you something. If I flipped this around and solved for the Ka of the conjugate acid of this buffer system, so I'm just going to put this in my calculator real quick, I get this. 5.88 times 10 to the negative 9th. If you'll recall from the previous slide, it said to prepare a buffer for a particular pH, you want to choose a buffer whose pKa, not pKb, pKa value is closest to your desired pH. Well, here's my desired pH. If I take the negative log of this Ka, that's going to give me my pKa, and that gives me this. pKa equals 8.23. I'm just showing you further why that statement on the previous slide is correct. If I use this particular buffer system, this using hydrazine and hydrazinium chloride is a good choice because its pKa is very close to my desired pH. Okay, so that's why I chose this particular buffer system. So I just wanted to show that to you. Now let's actually read the rest of the question. Okay, it says the buffer is accidentally prepared using 85% pure hydrazinium chloride instead of 99% pure. Assuming impurities in this solid are unreactive, explain how this error affects the pH and the capacity of the buffer. Okay, I'm actually going to go a little bit out of order, and I'm going to focus here. Because it's not the base that's affected, it's the amount of conjugate acid that's affected. If I'm only using 85% pure hydrazinium chloride, that means I'm going to have fewer moles of the conjugate acid. Okay, that means the capacity of this buffer is going to be less. If you have less of either player, either the base or the conjugate acid, the capacity is going to be less. Okay, so I can answer that question right away. Now let's talk about the pH. Base over acid. Okay, now which of these pieces, the base or the conjugate acid, is the one being affected? It's this one. Okay, so let's think mathematically. What is that going to do here? This is not going to change, and this is not going to change. Okay, let's think about this. If the denominator is going to get smaller, okay, think about it mathematically. It's like comparing the log of 1 divided by 4 to the log of 1 divided by 3. Okay, the denominator got smaller. What effect does that have? That makes this whole piece not quite as negative. Taking the log of numbers less than 1, like a fraction, 1 over 3, gives you a negative number. And that number is not going to be as negative. Okay, this would be a more negative number. So how is that going to affect the pH? You have to think about this sort of mathematically. Having the pKa plus a not as negative number is going to give us a higher pH. Okay, you can always plug in fake numbers to sort of prove your logic here. So if the ratio of base over conjugate acid was 1 over 4 and now it's 1 over 3, log of 1 over 3 is not as negative a number as log of 1 over 4. Taking the pKa and adding it to a not as negative number is going to result in a higher pH. The result of this mistake the student has made is going to result in a higher pH. I know that was a little bit tricky. So that wraps it up for Unit 8.10. And I hope you have learned a little something today, and I look forward to seeing you next time.